Infinite geometric series patterns can manifest themselves in very interesting ways, mathematical ways. I'm showing you here in this video one of those ways. An excellent example. I am Mr. Ish. Thank you for joining me. Our example here with regards to infinite geometric series relates to the 45-45-90 triangle. You know that's an isosceles right triangle. Two equal sides and a hypotenuse. We will do everything here in a very interesting manner. You're starting here with a isosceles right triangle. I'm not going to be drawing the 90-degree sign just so the depiction does not get too messy. I'm looking at everything here in a 1-to-1 to root 2 relationship, 1-1 and a root 2, 45-45-90 trigonometric ratio. You know that. The first two columns over here represents the legs of a triangle. The last column here will represent the hypotenuse. You will see interesting infinite geometric series patterns develop with regards to what you see. I have a 1, 1 and a root 2. I'll take the hypotenuse and I'm going to bisect it by means of a segment at 90 degrees in all instances. You see I've developed this little point over here. What was originally a right triangle has been separated into two different isosceles right triangles. A hypotenuse has been split in half, but what was originally a hypotenuse has now become a leg. We will only be focusing on one triangle at a time. The other one we'll always ignore. Here's the triangle I'm focusing at. Now I have a leg and a hypotenuse. This was originally my hypotenuse. Now this is my next hypotenuse. The original hypotenuse will now become, by means of its dimension reduced by half, the new leg. It will be a root 2 divided by 2 because the original hypotenuse was divided in half. But I can write this in a better way. Root 2 over 2 is the same thing as 1 over root 2. Since it's isosceles right triangle, the other leg is also 1 over root 2. 1 over root 2, 1 over root 2, and the next hypotenuse. What will this hypotenuse be? Well, take everything to the Pythagorean formula or do trigonometric ratios. 1 over root 2 square plus 1 over root 2 square, and square root of that, you'll get a 1. Now, from this point, I'm going to generate yet another isosceles right triangle that way. And now the previous hypotenuse has become two legs, but of course I'm focusing only on one triangle. This will be the next leg, 1 over 2. Obviously the other one is 1 over 2. Here's my 1 over 2, 1 over 2, and here's my next hypotenuse. This hypotenuse will obviously be easily determined. 1 over 2 square plus 1 over 2 square, and then the square root. You will have here a 1 over root 2. Now from here I'm going to generate yet another perpendicular. These are all perpendicular bisectors of the hypotenuse. And I've generated a new hypotenuse. The original hypotenuse has been split into sides, and that'll be 1 over 2 root 2. Each hypotenuse gets split into half, hence the next leg is always half of the original hypotenuse or the previous hypotenuse. And then obviously you can do this. It'll be 1 over 8 plus 1 over 8, and then square root to get this value right here. This here is a 2 over 8, which is a 1 over 4, and you're getting a 1 over 2. You can see a very interesting pattern is developing over here. It's an infinite geometric series pattern. I have 4 arrows. I have 4 of these. From here I'm developing yet another perpendicular bisector, and I've developed yet another hypotenuse. And you know this right here will be half. The new leg will be half of the original hypotenuse, and the other leg will be the same. And this right here must be the square root of the sum of these squared. 1 over 16 plus 1 over 16 square root, the Pythagorean formula. 2 over 16, which is 1 over 8 square root, it'll be 1 over 2 root 2. So we're developing a very interesting geometric series pattern. Here develop yet another. I have a new hypotenuse. I won't do any more because we'll extrapolate the rest. Develop another perpendicular bisector. I have another hypotenuse, do another one, and I've generated another hypotenuse. You see all of these ways we can generate an infinite geometric series by always taking an isosceles right triangle and bisecting the hypotenuse with the perpendicular bisecting segment and then continuing it forward. Now let's start analyzing these. The dimensions of these lengths are infinite geometric series. The dimension of the hypotenuse is infinite geometric series, and you can see it. There's a common ratio over here. In this column right here, the common ratio is 1 over root 2. Take any value and divide it by the value before. 1 over 4 divided by 1 over 2 root 2. I'm looking at these. It'll be 1 over 4 times 2 root 2 over 1. This is a 2. You have a root 2 over 2, which you simplify as a 1 over root 2. A common ratio here of a 1 over root 2 with regards to the legs. So common ratio with regards to the legs of the isosceles right triangle is 1 over root 2. It's convergent because it's a value less than 1. Now look at the hypotenuse values. Pick any two values. I'll just pick these two. I have a next value divided by the value before. You'll have 1 over 2 times root 2 over 1. You'll have a root 2 over 2, which is again 1 over root 2, and with the hypotenuse you have a common ratio here also of 1 over root 2. You're clearly seeing that the length dimensions of these right triangles, isosceles right triangles, and the hypotenuse dimensions are infinite geometric series. We can also formalize it by means of rule. With regards to the lengths, these are my values. I'm starting here with a 1. My rule would be n is equal to 0 up to infinity. I have 1 over root 2 to the power of n. Again, you can put exponent n in the denominator or entirely, it's all the same. When you expand this out, these are the values you'll get. 1, 1 over root 2, 1 over 2 onwards. With regards to the hypotenuse, our rule will be this. N is equal to 0, infinity. Our first item is a root 2. You'll do root 2 divided by root 2 exponent n. But you can clean that out. You can rewrite that in a better way using laws of exponents. By bringing the denominator expression up, you will have root 2 exponent 1 minus n. That will give you these set of values, the hypotenuse values. When n is equal to 0, you'll have root 2 to the power of 1, you'll get that. When n is equal to 1, you'll have root 2 to the power of 0, you'll have that. When n is equal to 2, you'll have 1 minus 2, which is a minus 1. You'll get the reciprocal and onwards. These are the two rules. Infinite geometric series are very well seen here in this phenomenon you have with regards to the lengths of the isosceles right triangles and with regards to the hypotenuse of the isosceles right triangles. A very interesting phenomenon I'm sharing with you here. Thank you. Have a good day. Bye.